Cynthia, will we have access to this recording after the meeting is over?
Yeah, just reach out to Eric Kwan, the person that set up the meeting, and he can send you the link for the recording.
Thank you so much.
Sure. All right. I think we might as well go ahead and get started. So I'll kick it off and then I'll turn it over to you, Kim. So just to remind everybody where we are, this is a technical conference for the National Grid Gas Long-Term Plan proceeding. Today we are going to have a presentation from some stakeholders on some thermal energy issues and some other topics. And then I guess we are open to taking questions during the presentation, right?
I thought maybe we could get through the presentation and then
Okay.
ask questions, but it's like if something feels really pressing and people need to stop, we're not going to, let's play it by ear.
Okay. All right. So why don't you go ahead and kick us off then? Thank you.
Okay, great. Thank you so much. Good day, everyone. I extend our sincerest gratitude to the DPS staff for co-hosting this technical conference with Sane Energy for Docket 24G0248, the Long-Term Gas System Plan for National Grid New York. Today, 4 esteemed presenters will share their valuable insights on key topics related to our gas system's future. Zeyneb Magavi, Executive Director of Home Energy Efficiency Team, or HEET. Ania Camargo, Associate Director of Thermal Networks at Building Decarbonization Coalition. Aaron Miller, Eastern Regional Manager of SHARC Energy for Wastewater Energy Recovery. And Jared Rodriguez, Principal at Emergent Urban Concepts. First, our presenters will discuss network geothermal systems, promising opportunities and successes. Next, we'll delve into climate emissions mandates and the future of gas proceedings nationwide. Following that, another technology that uses wastewater to create heat, cooling, and hot water in commercial, industrial, and residential buildings. And lastly, we'll emphasize the urgent need to retire the Greenpoint LNG facility in an orderly and rapid manner. We appreciate your attendance and we look forward to discussing these crucial issues. Please hold questions until the end, but you may submit them in the chat during the presentation or use the raise hand function for real-time interaction. I will now start sharing my screen and I'll pass it to Zeyneb to begin.
Thank you. Can you hear me okay?
Yeah, I'm just going to share my screen. There we go. Everybody can see it okay?
Yes, we can.
Yep.
Great. Okay. Take it away, Zeyneb, and just tell me when you want me to proceed to the next slide.
Thank you so much. And it's a pleasure to be here. And I appreciate having the chance to introduce the technology. For those of you who already know some of this, I apologize. It'll be over soon. So I want to start by just framing our conversation that the background to this first slide is the existing gas system in a New England region, and that it was bold and new in the 1800s. And we are in this very unique moment of really attempting to carefully, thoughtfully, in a data-based way, reimagine our energy system, which is what we are here to do today. So next slide. One of the largest opportunities that we have not entirely declared or put our eyes to is thermal energy, the thermal energy all around us. A recent IEA report, the first on geothermal in history, stated that the technical potential of geothermal would be more than enough to meet all heat demand and then they just listed continents. So this reality that there is a huge thermal reservoir all around us to tap is something we need to keep at the back of our minds as we look at our new energy system. Next slide. And I apologize, I have 2 slides on just some definitions around words because the words in this space are a little bit confusing. So one of those major sources of thermal energy in the world around us is called geothermal, and it refers to multiple different types of geothermal energy and geothermal technologies. So just to clarify today, if I use the word geothermal, I am only referring to the third and fourth in this chart, the geothermal heat pump or the geothermal network, both of which are the anywhere, everywhere geothermal energy. All geothermal provides stable, non-intermittent energy. But the shallow and low temp version that we are discussing today is everywhere and lower cost and lower risk. Next slide. The other form of thermal energy I want to draw attention to, which will get discussed later, is waste thermal. This is a all energy system diagram from Lawrence Berkeley Labs on the US energy system, and the majority of our energy is wasted, and a large portion of that is thermal energy. And so if you build what we are proposing, a thermal network, you have built a thermal market, and the waste thermal and the geothermal and other sources of thermal become energy assets. This is a new vision of a new energy utility. Thank you. Next slide. So what is it? Well, I'll just kind of take it apart really quickly. Really simply, there's the buildings, which have a heat pump. The most efficient form of heating and cooling is a heat pump. We have one in our refrigerators, but the most efficient heat pump is the ground source or geothermal heat pump. So if each building has one or many of those, which are connected to supply loops from a thermal energy network, which is the utility infrastructure in this utility, and it is pipes, HDPE typically, filled with water several feet underground, moving that water in loops in the street, and then delivering it to buildings and back. The water carries thermal energy. Sometimes the water has glycol, depending on the design. Where does that thermal energy come from? Well, a couple places. One form is the geothermal boreholes here pictured as an energy resource. Also, the other buildings sometimes provide thermal energy, but there are also other things like industrial waste heat, lakes, rivers, and ponds, and a surprisingly long list of thermal resources all around us. So the really interesting thing about this technology that's kind of risen in profile in recent years is that every component of it is old tech. It's been around, it's reliable, we have all the data. When you put them together this way with the single pipe ambient temperature loop, for example, then they become a new technology in the performance and outcomes, but without the risks of innovation. So also each of them can have different ownership or financing models, but we're not going to get into that today. We're just talking about the potential of the technology. Next slide. All right, so I want to make sure that in at least in some small part, you understand that the outcomes that are coming from the projects in the ground are not magic. Heat pumps themselves do have this slight air of magic. You put one unit of energy in and get multiple units out. How is that not magic? Well, if you count thermal energy and pay attention to thermal energy, suddenly it is not magic. When you build a thermal energy network as pictured here, and I have made it purple because here in Massachusetts, the spray paint on the street is purple for a thermal energy network or geothermal. And it has both heating and cooling, a large temperature range. And so we have on this picture, maybe it's a supermarket and it is cooling, which means it is pushing heat into the system, and the other buildings are heating. So that synchronous load cancellation is one piece of the efficiencies that stack up in this technology. It's one of the reasons that you get the outcomes. Next slide. If you add, for example, geothermal boreholes, that provides a degree of storage that can create load canceling day to day, week to week, and month to month. I call that asynchronous load cancellation. When you add that aspect, you get another degree of efficiency. There are more that stack up, including the efficiency that comes from the thermal storage in the loop. But I just wanted to give some window into the reality of putting these simple components together and getting a more efficient technology out the other side. Next slide. The other key aspect I want to make sure you have is that when you build these as a single pipe ambient temperature loop, as the thermal energy network and geothermal networks are predominantly today. This can grow flexibly over time, both in extent and in number of customers. In other words, it has a utility growth model, unlike many district energy systems designed in the past. So this, for example, can scale through to create a thermal utility. And when you get to scale, you have also incidentally built a large thermal storage capacity. Next slide. And that is part of what drives one of the most interesting outcomes of this heating and cooling technology, and that is that this heating and cooling technology has an enormous impact on the grid. The curve on the left, I call the Falcon curve because it is scarier than the duck curve. It's a January to January, all buildings US electric demand curve. And the green is today, or rather, actually, it was a couple years ago when we published this. And each of the colored curves is what it would look like if we move fossil fuel building use to electricity, but each one is a different technology. And what this curve is about is saying that the choice of technology of electrification of buildings determines the impact on the electric grid. It matters a lot. It matters to cost, it matters to outcomes, it matters to feasibility. And as you can see, going to geothermal heat pumps and or to network geothermal brings the winter peak down and flattens the load and improves the load factor for the electric grid. And that has driven that outcome or impact is part of why the Department of Energy published last year a research paper on the grid impacts of geothermal heat pumps. And with a mass deployment, which they counted as 68%, they predicted $1.5 trillion in savings by 2050 between a move from air source to ground source heat pumps. That included a 38% reduction in transmission lines and a 12% reduction in wholesale electricity price. So that scale of impact is mind-boggling, and it's really critical to understand as we make large decisions for how to move our energy system forward. Next slide. The other thing I think is critical to think about in the design of this is that thermal utility can move customers from gas to geo while keeping them in a merged ratepayer base, which is what we are moving forward with in Massachusetts to date. And that has the opportunity to stabilize the ratepayer base, keeping energy bills from spiking on as we move off gas. Next slide. This is from a report by Massachusetts gas utilities for the future of gas docket. And the most scary projection is the building by building off gas, and the least energy burden for low-income customers was a scenario that actually only had a portion of geothermal networks, but that portion was enough to lower the energy burden for the low income. Next slide. So in really quick summary, and I'm happy to take questions later, the projects that are in the ground today, including the first gas utility install of this technology and many other campus and development installs, have already demonstrated the following outcomes. Of course, this is an engineered solution, so it does depend on the engineering, the rate making, the policy. Any of these are relevant to talk about. Next slide. But I want to talk about scaling. So these outcomes, the potential, have driven a lot of interest. And just at the last COP29, there was a Financial Times video with the head of the IEA and leaders from the World Bank on the extraordinary potential of this technology, declaring it the waking of a sleeping giant. Next slide. And myself, I was last week in Pakistan, where I had the unusual opportunity to observe a electric and gas grid in crisis, both worried about death spirals, with a buying LNG on the spot market and so on. in that country and in countries listed, Turkey, Kyrgyzstan, and Jordan, the World Bank has initiated projects and is paying for the feasibility and design that are significantly larger load than the LNG plant in discussion today. And I want to say that because I think that it is important to understand that this technology is considered ready for that scale. So next slide. And to end, there's been a lot of buzz. I think it comes down to the following things. The technology of thermal energy networks taps ignored but ubiquitous energy resources. They are new, yet ready now, and they multi-solve our electric grid challenges, our water shortages, security concerns, health, and more. So next slide. It's the last one. So one of the things that I have most enjoyed about the technology is it brings a lot of different entities together to do that multi-solving and to reimagine and rebuild the electric system. I mean, sorry, the energy system we need for the future. So I turn it over to the rest of my colleagues, and I look forward to your questions.
Thank you so much. We'll turn it over to Ania now.
Thank you so much. Ania Camargo, and I'm with the BDC, which is a national nonprofit that works with all stakeholders to decarbonize buildings. And so my talk is going to be about the sort of giving you all a national landscape on what's going on with thermal energy networks, and then ending with how it affects New York. So next slide, please. So the country is decarbonizing. The states in light blue are those that have emissions reductions commitments of 75% or more, and RPS, or greening the grid commitments. As you can see, there's a lot of them. Because about a third of our emissions are about buildings, it becomes like, how do we reduce emissions in buildings? And so next slide, please. The primary strategy that most states are using is to incentivize the installation of air source heat pumps, and Americans are buying more air source heat pumps than ever before. And they've surpassed the gas furnaces in the US for the last 3 years in a row and are expected to continue. And New York in particular is one of the states that committed to quadrupling the installation of air source heat pumps by 2030. And so that is really awesome in a lot of ways, but it also creates some challenges. Next slide. So as you see here, you see some houses have randomly decided to install an air source heat pump, and this is a one house at a time approach. It's an unmanaged transition. So what ends up happening is that fewer and fewer homes or buildings are left on the gas system, having to cover the whole fixed cost of the gas system. Usually the folks who are electrifying their homes are the folks who can afford it or own their properties, and the ones who can't and are renters are the ones that are least able to pay for it, so are covering these costs. And so that becomes an enormous equity challenge, and of course a big concern for particularly gas utilities. And next slide, please. At the same time, we are seeing that gas companies are, we have very old, as I think Zeyneb said, the last century technology. So we have very old gas pipe, particularly in the Northeast. And gas companies are replacing leak-prone gas pipe with new gas pipe at an enormous cost. As you can see on the right, there's been some analysis that have been done. In New York is on track to spend $28 billion replacing gas pipe by 2043. And so similar to the question we have today, it becomes like, do we really want to be spending billions of dollars on infrastructure that we will not be using in the near future, or is there not an alternative? And so for these and other reasons, HEET, and particularly Zeyneb Magavi, came up with the idea, hey, instead of replacing gas pipe with new gas pipe, is there something we could do that's better than that? And came up with the idea of geothermal networks. So next slide. I won't go into this because Zeyneb already did. All I'd say is that you see at the top there, it says thermal energy networks and then geothermal networks. So the technology that would work best in terms of expandability and interoperability would be these geothermal networks. But I am looking at thermal energy networks in the bigger scheme as different states across the country are considering different designs as well. Next slide, please. And as we were saying, this is not new technology. There are many of these thermal energy network sites across the country, at least 100 that we have identified. And this map includes all of the different types of designs and shows different, there are also different ownership models, and there's different, there are different stages of development, but you can see there are many. The design that Zeynep talked about, there's one in operation since 2008. So again, not new technology. What is new is asking utilities to build these. And the thing about them is that right now, anyone can build these systems. And this is why we're seeing them across college campuses and in some communities. The only ones who are not allowed to are utility companies, both gas and electric. And that's because they're highly regulated. And usually, like for a gas company, they're only legally allowed to sell gas. And so to be able to allow them to tap into this technology, we have to pass legislation. So next slide, please. So far, 8 states have passed legislation that either mandate or allow gas utilities to install thermal energy pilots. You can see them there listed on the right side. New York passed the Utility Thermal Energy Network and Jobs Act in 2022. It was an incredibly comprehensive bill, and the majority of the states that followed used the model of New York. And the thing that's really big about it is that it mandated that all of the largest utilities, 7 largest utilities, at least 1 and up to 5 thermal energy network pilots. So that's what that is currently underway. And then other states, you can see, have filed legislation this year. And so we are expecting to have more states that have passed thermal energy network legislation by the end of 2025. Next slide, please. And so sort of on a parallel track, also related to emissions, there's this regulatory process happening where regulatory commissions across the country are starting or in the process of working on future of gas proceedings. So far, 13 states in the District of Columbia are doing this. And they are basically, the commissions are saying to utilities, all right, we have to meet this emissions mandates. How are you planning to do that? Which is, again, part of this long-term planning process. And next slide, please. We are seeing some themes emerge from across the country. This is, they're nicely summarized by E3 in this diagram that they did for California. A lot of the same things, right? So limiting expansion, really evaluate all new gas infrastructure, looking at alternatives, integrated planning, the gas planning process. Many of these states are saying thermal energy networks are a very important pathway for gas utilities, particularly to be able to meet these climate mandates. And so just as an example, Massachusetts has wrapped up this process. Their 2080 order that came out, I think, last year, says that for all new gas infrastructure, the gas utilities have to consider non-pipe alternatives, including thermal energy networks, and they're asking for electrification, neighborhood scale electrification pilots, not only thermal energy networks, but also air source heat pump pilots. And then a couple of weeks ago in Colorado, a small gas utility was ordered to support neighborhood scale electrification projects and was given money to actually do a feasibility study of a thermal energy network. So this is part of what we're seeing, is that it's not only at the legislative side, but at the regulatory side as well. And so next slide, please. So what does this mean for utilities, both gas and electric, but I will focus here a little bit more on gas. It is a very similar business model, but in some ways a better business model. Of course, avoided stranded assets, which we were talking about, like if you're replacing the pipe with something that we're going to be able to use over the next 50 years. It's a really valuable path for the existing utility workers with minimal retraining. The gas pipe and the water pipe are the exact same material. And important for today's discussion, it is hyper local. So it's not only local energy, but it's local control. You don't have to worry about what happens upstream. You don't have to worry about extreme temperature. This is completely locally controlled, and it leads to that next point, no price volatility. Doesn't matter, again, what the temperature is or how much is available, because thermal energy is always available, and the geopolitics don't affect the price. It's safer because it's just water. Zeynep touched on the really important impact to electric grid. It's a year-round business model, not just heating. It is both heating and cooling. And then there are some pretty important state incentives, definitely in New York, and federal incentives. There's an investor tax credit that can be between 30 and 50% of a project. So next slide. So utility companies, both gas and electric, are very interested in this technology. There is a utility net geo collaborative that has 28 utilities that represent about 45% of the gas customers in the country. And those states in light blue are where gas utilities have proposed a pilot to their regulatory commission. So far, there are 24 pilot proposals that have been made. Next slide, please. And very importantly, the first pilot has already gone in the ground. You all have probably heard of the thermal energy network in Framingham, Massachusetts that Eversource put in that went live last June. It's an environmental justice community, 37 buildings, 140 customers. You can see there's that green loop in the map is about a mile of pipe, and the little orange cones are 3 bore fields with like about 90 bores. And they converted whoever signed up to be a part of this. So it could be gas, oil, and resistance heat. And to make Zeynep's point, they are estimating that the total load for this neighborhood will actually go down because they converted some of the houses that had resistance heat. It also includes commercial and residential and several affordable housing buildings. And then, as you know, from a cost perspective, because this is a utility model, it allows spreading the cost across all gas customers and across time, making this really affordable to the folks who are hooked up to this. And then my last bullet here is really important, which is the learnings. This is the first project, and HEET is working with Eversource and documenting everything about this project. And so there's a lot of learning that is coming out. Eversource has also been very generous sharing their learnings. And there's a second loop coming, and applying all of those learnings, already it looks like the cost for the same size, roughly the same size, the cost will be about 55%. So that is where we are sort of in that process. And next slide, please. And that brings us to New York. So New York is incredible in what you all are doing, because again, you're doing this at big scale. So 14 pilots have been filed, but 11 projects have moved to stage 2. And we are expecting that the final engineering designs will come in the summer or in the fall. You can see that there's 3 national grid pilots, and there's also 3 Con Ed. Remember when I said the bill allows them to have up to 5, so we could actually have 2 more for national grid and 2 more for Con Ed for this territory, which would be, again, impacting the amount of gas needed. And I want to highlight there's a Con Ed project in Mount Vernon that is actually planning to retire a portion of their main. So it's an opportunity to test this idea of avoided main replacement. And it's also going to remove some of the gas demand, which would also help this Greenpoint area. And this is the kind of thing that we are going to be able to see as these projects get put in the ground, which is really exciting. Next slide, please. And I want to end with this, which is New York has enormous opportunities for thermal energy networks because of all of the sort of interest in decarbonization and your commitment to your climate plans. You can see here at the top, in addition to the thermal energy networks, New York is leading by example by decarbonizing their state facilities like the SUNY and CUNY campuses. The Governor Environmental Bond Bill that just came out includes $150 million for electrification, including $100 million for the SUNY campus. And then there's also several municipalities that are looking at thermal energy networks as a way to decarbonize. And then on the electric side, because of that, oops, sorry, can you go back up just a minute? Because these are the most efficient systems available today to us, the NIPA decarb action plans, the Local Law 97 and All Electric Buildings Act all are counting on TENS, or including TENS, as a way to be able to meet their goals. And the Grid of the Future docket is going to be studying TENS to look at energy storage, at waste heat recovery, and really figuring out how can we use thermal energy networks as a way to save, to flatten the peak, and using it as a tool for the electric grid. So the bottom line is that the implementation of TENS in New York will not only decrease how much gas we're going to need, but also decrease the necessary build out of the electric grid. Thank you so much.
Thank you so much, Ania. Now we'll pass it over to Aaron Miller, the Eastern Regional Manager of SHARC Energy.
Hello, thanks. I'm going to try to keep a good pace here. If you could go to my first slide. So wastewater energy transfer. So I'm with SHARC Energy. We're a Canadian company. We are harvesting energy out of wastewater. That's sanitary water before it leaves a building, or sanitary water as it passes through a municipal pipe, a wastewater treatment plant, lift station, doesn't matter. The more we have access to, the more energy we can harvest, obviously. My marketing guys love this slide because it demonstrates just how much energy is being wasted on an annualized basis. And to give you some context, New York City DEP handles 1.3 billion gallons of wastewater every single day. And the rule of thumb is 1 million gallons of wastewater a day equals 1 megawatt of thermal energy. So New York City alone is flushing 1,300 megawatts of energy every single day. Just to put it in context, I think Indian Point was somewhere around 2,000 megawatts. So over, half the capacity of that plant is wasted every day. We're just trying to capture a portion of that energy, reuse it for a few minutes, and then send it on its way. Next slide, please. The reason why we have so much wastewater is because people like me take 2 screaming hot showers every day of the year. It doesn't matter what time. So we have really consistent temperatures. The average temperature coming out of a multifamily residential building is 70 degrees year round. It does not matter. You can mix in cold water from sinks and toilets. It's all about 70 degrees. If you add amenities like a restaurant or a gym or a pool, you can take that up to 80, 90 degrees. And again, just increasing the capacity of that, of that wastewater stream. The differentiation of our technology is that it's completely sealed. So we're working with black and gray waters, raw sewage, and we can work with it inside of a building envelope. There's no odor, there's no cross-contamination. So it really opens up the ability to do wastewater energy transfer at the building level as well as the district level. It's what we're talking about today. Next slide, please. And I'm going to forego a whole slew of technical slides, and I welcome the opportunity to walk everybody through how these 2 technologies work. But this one slide shows our 2 boxes, and we have variations on a theme within each of these categories, the Piranha and the SHARC. And it really comes down to scale. And just to keep it simple, multifamily residential buildings, the Piranha, which is really a water-to-water heat pump. I'm sure you guys know how heat pumps work. We're basically harvesting energy from water and making potable hot water. We're just using a different type of energy source. We've got a tank inside this thing that allows us to fill it with that 70 some odd degree wastewater and slowly extract the energy over the day, put it into a refrigeration cycle, move it through a potable heat exchanger, and give you 140 degree hot water all day, every day. And this is, you can see at the bottom, repeatable, scalable, and circular. Because what we can do here is the same thing we do in this building, we just literally, boom, next building. And then you can scale it up. If you have a building down the street that's 3 times the size, you just scale it up. And it's circular in so much that the Piranha, if you can allow me to capture 100% of the wastewater before it leaves a building, we can provide 91% of the domestic hot water for that building. It really is a true 1-for-1 ratio. But beyond multifamily res, as you can see through in the white section here, all of these market sectors make a lot of hot water waste and have large loads, heating, cooling, domestic hot water loads. And by balancing the 2 of those over these large district systems, we can really extract the most efficiency while we heat, cool, and make hot water for these buildings. And on the right side of my screen, I just want to real quick, the SHARC is really get down to it, it's a specialized heat exchanger with wide gap plate and frame that allows us to run sludge through it essentially. And on the front end, we've got a specialized filter that removes enough of the large solids out that we can move that wastewater through the heat exchanger, do our thermal transfer without everything getting jammed up. And knock wood, in 15 plus years of operation, we've never once had to open up a machine for jamming. So next slide, please. I want to spend most of my time talking about actual projects that are being built right now. These are 3 that are happening in New York right now, Amalgamated, and they're all part of the Empire Building Challenge. Amalgamated Housing Corporation, We're basically taking the wastewater before it leaves the buildings, running it through the Piranha system, and we're going to provide around 95% of the domestic hot water for these two buildings simply using the wastewater they're already producing. It's brilliant. Whitney Young Manor is a little more complicated, larger building, and there's a whole hydronic refresh on this building. New facade, new hydronics inside, and they're actually excavating out of the ground enough space for a wastewater holding tank to create a thermal battery so that they can use the wastewater from these buildings to support an entire hydronic system. As you can see, the reductions in the carbon, these buildings are all basically subject to the local law 97 law and carbon taxes. So these are massive savings on the carbon side, as well as the energy efficiency side. And the one that's really exciting is Alafia. It's up and running right now, phase 1A. In fact, if you want to go to the next slide, I think it's on this one. Phase 1A is one smaller building with, as you can see, two Piranha serving a building that's connected to 35 boreholes. And then across the street, or literally across the parking lot, is two larger towers with a common lobby that are supported by a SHARC 660. Now, Salas O'Brien did an analysis for this complex, and there's actually a webinar from IGSPA that I'd be happy to share. You can hunt it down yourself. Brian Erlaub did a great presentation. He talked about those two large towers. Originally, when they looked at these towers, they're passive house design, net zero ready, so they're very cooling dominant. They don't need a lot of heat. So originally, they needed 125 boreholes at 500 feet to cover the thermal load of these buildings. By putting the SHARC into the loop, and this is wild, only picking up the peak cooling loads from those 5 or 6 or 7 really, really hot days allowed them to right size the bore field from 125 down to 93. So that's about a $500,000 to $600,000 first cost savings. Boom, right off the top. Brilliant. And now moving forward, as the climate warms and as the load profiles of these buildings change, and you tend to see those fields drift out of the optimal temperature range, not a problem. We're going to use the sanitary from the SHARC to temper that loop, pushing and pulling energy in and out of that loop as needed from the sanitary to keep that loop in the ideal temperature range. So over the course of the life, 10, 15, 20 years, you don't have to recommission. You don't need to dig more holes. You don't need to put a cooling tower on. You just use the sanitary that's the building's already making to keep that loop in the ideal fashion. So it really is a brilliant project. We're already working on phase 1B, phase 2. Ultimately, they're going to have, as you see, 2,400 affordable homes in these pods that are connected to individual loops. And then the plan is to connect all of those pods with a single ambient loop ATL that we will then tie the whole campus together. I'm thrilled. Next slide, please. And we'll be able to take you guys on tour. I think we're trying to get a Nessie Pro Tour of this in the summertime, so stay tuned. This is another district system out in Vancouver, originally designed for the 2010 Winter Olympics. Not our tech. It was having problems. They came in and put our technology in there. And as you can see in this yellow box, we were using two SHARC 880s to provide 180 degrees Fahrenheit for a hot water loop for 5 million square feet of a section of Vancouver. It was so successful that, again, scalable. Here's that scalable over time. We took these two out. We just commissioned 5, and we're now providing heating for 23 million square feet of Vancouver simply using the sewer. And what's really neat is Alafia, the previous slide, privately owned. This is a standalone utility. It's self-sufficient, doesn't take any incentives, any dollars from the province or the country. All the ratepayers are supporting this loop. So again, very efficient way to connect buildings and share the burden. Next slide, please. This is an ESCO model. This is out in National Western Center in Denver, old rodeo stockyard that they've repurposed for a multi-use campus. And this is a really cool gig. We now, as you can see in that bottom picture, we've got two SHARC 880s providing 3.8 roughly megawatts of energy to a district loop that supports a multi-use campus, about 1 million square feet of mixed-use space. This, as you can see, this barn, there's a lot more space in front of those other SHARCs because it's built to add more units as the more buildings get commissioned on. What's wild about this is, again, because there's so much space in this barn, the utility, the ESCO, the city, they all host galas, they serve drinks, they serve food. And then about halfway through the meal, they say, by the way, while you're enjoying your can of peas, look behind you, there's about 4,000 gallons of raw sewage running behind your head, and you have no idea because it runs about 68 dB, has no odor. So it's really quite brilliant. And this system demonstrates the value of, and the Lelum project I'm about to show you, demonstrates the value of thermal energy networks, because in the shoulder seasons, the loop itself self-sustains, because you've got, let's say, a supermarket on the one end of the loop rejecting 100% of heat into the loop, but on this end you've got multifamily residential doing a little bit of heating and cooling. I've got an aquatic center doing nothing but heat pull out of the loop. So by pushing and pulling and having this diverse mix of buildings connected to the loop itself stays kind of self-tempered. We just use the SHARC to push and pull a little bit of energy to make sure it stays in that ideal range, 58 to 78 throughout the year. And then in the winter and summer months, we ramp it up, and we either take a lot of heat out, dump it to the sewer, or push it in as we need it. Next slide, please. Lelum Village. This is an exciting project. This is, again, another privately owned Vancouver gave back, I should say, to the First Nations, a section of land that they had originally stolen from them. And they're building this mixed-use campus, as you can see here. This one little SHARC 60, this is our baby SHARC, is providing all of the energy required to support the existing 1.3 million square feet of indoor space right now. Again, as you can see, there's additional space, and those two blue containers behind the SHARC, those are wastewater holding tanks. Those are the batteries. They are 3 times the size they need to be, because they're planning to expand this out to about 3 or 4 million square feet of space. So when you can start from the beginning, you can plan for that expansion. Again, remember, it's scalable, it's repeatable, and it's circular. And what's wild is this is a great model. It's so efficient, the loop. It basically costs the central plant $4 per end user to operate per month. So what they do is everybody on the loop pays $20 a month. It doesn't matter if you're a supermarket, it doesn't matter if you're just a small business. $20 a month covers your nut, and then they take the $16 extra and they put it into a revolving fund that's going to help to finance the next phase. And it's so efficient that they have planned out, and again, we love geothermal. We loved, as I mentioned before, we're able to offset that geofield and condition it through the life of the system. They've planned for geopods around this campus. They don't think they're going to need them because the wastewater is so efficient. And with all due love to my geothermal friends, we're about a third, or 3 or 4 times as efficient and about half the cost. So it really is quite special what we've got going on here. So I don't believe I have any more slides. Like I said, I'm more than, I lied. Last one, let me finish strong. DC Water Headquarters. This is a standalone building, but I wanted to bring it up because I know that Ania and Zeyneb also mentioned this, the water conservation. This is the headquarters for DC Water, the sewer authority for Washington, DC. They've built this big green glass building on top of a lift station that handles 5 million gallons of wastewater a day. So we've got 5 megawatts of thermal energy to work with. It's really quite brilliant. The trick is, because this building is all glass and because of its orientation on the Anacostia River, it's in cooling mode almost the entire year. So we reject 100% of that rejected heat from the chiller plant into the sewer. Thereby, we think we're saving them roughly 1.5 million gallons of fresh water a year, which is why the US military and the government is really taking a hard look at this because of grid resiliency and water scarcity. You think about it, a building like this or a lift station in the middle of a community, especially in a disadvantaged community, you can now, in a complete grid outage with a small generator or a small battery, keep some pumps moving to rotate to move some ambient water. You can use this building now as the hub of a thermal microgrid, if you will, to provide grid resiliency, heating, cooling, and hot water for people during a complete grid outage. So there's a lot of really good ancillary benefits in addition to the energy savings, water savings, and as we've discussed. So again, really excited to be here and would love to take you guys on tours of all of these projects. They're all available for tours. And like I said, I would love to dive into a more technical conversation with anybody who's interested. So thank you for having me.
Thank you so much, Aaron. We are now going to move to Jared Rodriguez, the principal at Emergent Urban Concepts. Take it away, Jared.
Hey there, and I might not have camera. Let me see. Hold on. Okay. How is everybody? So good to see all of my friends on the phone here. I see a lot of familiar names. Pretty exciting. So I'm going to zoom out a little bit and talk about a concept or a thinking framework called resource efficient decarbonization and applying that framework to the neighborhood scale. And we're thinking about this at the neighborhood scale in a sort of rational way to consider the phase out of what could be stranded gas assets in order to accelerate gas asset retirement, which is sort of, I think, the issue that we're faced with today. So next slide. So I am the principal of Emergent Urban Concepts. I come from the commercial real estate world. I've represented a very large commercial real estate firm in various regulatory proceedings, have interacted with a few folks on the phone here in previous rate cases, helped to sort of establish the regulatory theory that has fed gas demand response to non-pipe alternatives, to this consideration of thermal energy networks, and now thermal energy networks sort of interacting with both the gas system and the electric network. I've responded to an RFP with the North Central Queens MTA, which is really exciting, and kind of introduced some of the concepts that I'll share here. And, you know, continuing to work with various organizations across the state of New York, whether those are advocacy organizations, utilities themselves, you know, additional entities, including state entities that are focused on accelerating neighborhood scale decarbonization. So next slide, please. So, you know, what are we doing really at the highest level? We're balancing multiple stakeholder goals to implement incremental change, right? We don't do these things in wholesale ways, right? Like we can't change an entire urban environment, that complex urban environment overnight. But things have to be on a trajectory, and we have to do our best to balance pretty diverse sets of goals. And you know, we've seen these particular goals across lots of different topics, but importantly, I think they're you know, very applicable to the energy transition. So how do we balance these issues, right, as we move forward with transition of the urban environment? So next slide, please. So resource efficient decarbonization, what is it, right? I mentioned that in the title slide. It's effectively a thinking framework or a heuristic for considering how buildings will transition over time away from fossil fuels, right? This all or nothing sort of fallacy that's out there isn't helpful, right? Buildings are complex. Each building is different. People don't like this, but every building is a unicorn, and they're owned by different folks with different goals. So it's a unicorn upon a unicorn, and then every neighborhood is a unicorn. So, you know, we often hear, well, what about like replicable solutions or strategies that we can just kind of stamp out all over the place? Not really. I mean, it's more about what is the building and what fits the building and what fits the people in that building and in that neighborhood. So what's replicable? It's the approach that's replicable, not the specific solution for the building, because we're not trying to shoehorn particular things in here. So what is RED, right? It's a strategic reduction in energy loads after you understand everything about the building, right? How does the building consume fossil fuel, when, where, how, and why, and across the year, right? When and how much when, and under what conditions. So understand that, understand how the building functions, how it acts. Then strategically reduce loads. So we've been doing this forever, right? With energy conservation and efficiency. You know, just because we're electrifying doesn't mean this goes away. In fact, it gets more and more important. And we've heard a little bit about that today from the other speakers, in particular, you know, from Aaron talking about waste heat recovery, and I'll talk a little bit more about that. But there's plenty of places in a building, especially commercial buildings, for example, where heat is purposefully wasted. You know, it goes down the drain or it goes out a cooling tower. So if we could capture that heat and circulate it back into a building, we can make very big strides toward reducing energy consumption. And strategically, we can implement partial load electrification, so strategic electrification for the easiest to electrify loads. And typically we start with domestic hot water, and then we work up toward the peak load or full electrification by layering in thermal energy storage and multiple sources of waste heat and multiple different technologies in order to most optimally and most efficiently achieve electrification versus putting in something that, you know, might not fit the building well and doing it all at once. So next slide, please. So other methods and strategies related to RED, again, reducing those loads, making the appropriate improvements to building facade, for example, reconfiguring thermal energy distribution throughout buildings to lower temperature distribution, recovering waste heat, making waste heat the primary heating source, and then supplementing it, similar to what Aaron was describing earlier and similar to what Zeyneb had described, and then tapping those and or sharing waste heat resources with adjacent buildings, for example, and then we start to get into these network solutions. Next slide. And so Zeyneb kind of mentioned this a little bit. You know, heating really is the elephant in the room, and it's not something that we in the sort of climate action and energy action world have focused on so much, right? It doesn't really get the attention, but in fact it should, right? Because buildings emissions, especially in New York, are really driving the entire urban environment emissions profile. And so we need to be focused on heating. In fact, it needs to be the primary focus in buildings if we're going to start to make this transition work. So really, again, it starts toward enabling steps. It starts with enabling steps, moving to that lower temperature distribution, choosing technology neutral distribution systems, low temperature hydronics. Hydronics are technology neutral in that any source of heat can plug in over time. Any type of thermal energy storage could plug in over time. Steam is out, water is in. So again, we're moving away from these high temperature distribution systems, and high temperatures typically require combustion and fossil fuel. So if we move toward those lower temperature distribution systems, we can incorporate heat pumps in a much easier way. And location is everything. So taking those enabling steps, moving equipment to the appropriate location, either for resilience purposes or for setting yourself up for additional retrofits in the future, is critically important. Leveraging these trigger points inside of building assets, right? Maybe I'm renovating an entire floor, or I'm repurposing a building, or I'm converting a commercial building to residential. Those are trigger points when these investments need to happen. You don't want to miss that window. So next slide. And all paths toward a resource efficient decarbonization include heat recovery and thermal recycling. So, you know, heat goes down the drain. That's the second one here. That is Aaron's business, capturing heat either on an individual building basis or from lift stations across a neighborhood or from a central wastewater treatment plant. We can capture heat and get it back to buildings, so we're reducing on-site loads. Cooling produces heat, right? So folks often forget about that. There are cooling towers that run in New York City year-round, right? Especially where there are high internal loads or there are glass buildings that have very high solar heat gain on the south side of the building. Those cooling towers are running, they're rejecting heat while at the same time burning gas to heat the north side of the building. So, you know, this is generally unacceptable. We have to be capturing this heat and getting it back into the building. So think twice about ventilation, right? We see a lot of hospital buildings that use 100% outside air. When you bring in, you know, outside air, you have to condition it. And then when you reject air through ventilation, right, through exhaust air, you're losing all that heat. So why not capture the heat and add it to the incoming fresh air? And save it for later. So to the extent that we're recovering heat, we can incorporate whole variety of thermal energy storage technologies in order to capture that heat and save it for when we are reaching peaking load. So next slide. Now, effectively what Greenpoint does, right, or should do. Resource efficient decarbonization. So critical aspect here, and we heard this from Zeyneb earlier, networked hydronic systems can move thermal energy resources of a variety of typologies from one building to the next when heat is needed most, right? And so that is the basis for a thermal energy network. We can be capturing heat from across the urban environment, implementing resource efficient decarbonization in a phased and rational incremental way across a whole variety of building typologies and neighborhood typologies in order to strategically reduce gas consumption and drive decarbonization and the energy transition. So next slide. And so again, neighborhoods offer different thermal energy resources, and we've heard this as well from the other speakers. There are a number of ways to have the thermal energy system interact with the electric system in an optimized way where perhaps excess renewables are being captured and stored as heat for distribution later on for that peaking period. As we increase the temperature of the distribution network, right, this thermal distribution network, we're also driving down the electric consumption of the heat pumps that are using that thermal distribution network. So we can modulate the electricity consumption and provide strategic electric demand response through the use and the deployment of waste heat resources, thermal energy storage, and thermal energy network. So next slide. So I mentioned neighborhood scale decarbonization, or zonal decarbonization is another concept here. We're already really thinking about this, I think, deeply through non-pipe alternatives and non-wires alternatives, right? So if we take that concept of a particular zone that's going to receive lots of investment in order to drive a particular outcome, and we expand that to the concept of decarbonization, we can then begin to integrate lots of other goals, right, into that strategy. And those goals could be a focus on jobs, economic development, housing production, retirement of gas assets, revitalization of neighborhoods, transition of communities away from fossil fuel. So thermal energy networks and shared infrastructure, this is really vital to achieving neighborhood scale decarbonization and accelerating the pace of this transition. Next slide. And so now here's another concept that, folks that are familiar with the electric grid understand, economic dispatch of power generating resources. I'm not suggesting that we're literally in real time dispatching thermal energy resources into a network, but we can think about the deployment of particular measures within the context of resource efficient decarbonization as a thermal energy dispatch in order to achieve the retirement of this Greenpoint facility. So next slide. And so we can use that thermal dispatch approach to radically reduce that peaking gas throughput, right? Which is, exactly the issue that we're trying to get at here in order to reduce the amount of redundancy that we have in our gas system and improve resiliency, right, against these extreme cold weather events that could be coming. So, actually back one. So in this case, right, the dispatch could look like, so similarly to renewables, which are the cheapest form of power production, insulation and energy conservation measures should be dispatched first, right? Controls could be dispatched across the system in order to help modulate that demand during the peaking period, for example. Partial electrification, I said target domestic hot water, right? That can shave off another layer of the peaking demand during the winter or during that design day period. Thermal energy storage can do that quite dramatically. It could shift across an entire day in a diurnal way, or it could even shift across months or seasons And then as we get to full electrification, we're disconnecting entire buildings from the gas system and reducing those loads. Right? So another way of sort of getting beyond being stuck, right, when it comes to some of these things, is to shift your mind away from all or nothing catastrophic framing, right? All or nothing thinking, really, when it comes to this transition, is the thing that gets us stuck. And we have to get behind these faulty assumptions. So reducing our peaking throughput, as associated with the Greenpoint facility, does not equal fully electrifying 291,000 poorly electrified homes, driving that peaking electric demand up. We don't need to do that, right? We could take those strategic, rational, incremental steps across perhaps larger buildings, instead of single family homes, to achieve the same throughput reduction. Neighborhood scale solutions like thermal energy networks, they can operate at up to 5 times the performance of previous electrification projections, right? And those are typically incorporating air source heat pumps, and air source heat pumps operating at relatively low efficiency during very cold periods, right? This is where that coefficient of performance comes in that Zeyneb was mentioning earlier. So if we're strategically deploying this shared infrastructure, and we're incorporating thermal energy storage and the ability to modulate demand coming from heat pumps, we could operate this system at much higher capacities during these extreme periods of cold. So geothermal and thermal energy networks, right, can electrify these buildings and produce a grid peak lower than the current summer peak. We know that. We know geothermal systems can do that, and thermal energy networks are even better than that. So that is sort of settled science here, right? Like, we're seeing systems operate that can even reduce summer peaking loads, right? Only 6 years ago, we didn't know that that was possible, but it is. And requiring the least cost approach really is a necessity, and this goes back to that economic dispatch of thermal energy resources. So next slide. And I think I'm going to end here. I actually have some case studies that we might be able to talk through in the questions, some of which actually Aaron hit on through the Empire Building Challenge work. But here are some really high-level steps to move beyond this facility that needs a particularly large amount of investment if it were to continue in its capacity and its function. So implementing those strategic gas capacity reductions across the territory is important, but zooming into specific neighborhoods where multiple goals are to be met, right? In order to leverage these investments to achieve other outcomes, again, housing production, economic goals, sector coupling between hospitals and data centers, right? Layering those goals together in a very strategic way in specific neighborhoods within the territory can address these non-pipe alternative ideas and non-wires alternative ideas simultaneously. Then, the next thing would be to, in order to further that, right, within those specific neighborhoods, conduct that zonal market-based tender, right, to go out to the market to deliver the capacity, right? Think about delivering that economic dispatch across possibly multiple vendors. Could be hundreds of vendors, responding to a tender within this particular neighborhood to achieve that strategic reduction of peaking gas throughput. This is a big one, but the idea that we could de-risk and decouple the environmental remediation costs at this site from the rate base and the company might be something that we all have to step back and think about in order to unstick this issue. Just thinking broad brush, high level here. And then unlocking that land value at this location to recover some of these costs and to create additional NPA peaking capacity is something that I think we should very seriously consider and perhaps, set up a working group to start thinking about how that might happen. And I'll end here. So thanks.
Thank you so much, Jared. I'll pass it back over to Cynthia.
Okay, before we ask for people to raise their hands, there was one question in the chat. So I don't know if everybody can see that. I'll read it. It was from Chris Stolicki of staff on the Framingham system. He was asking for some cost information. And then what happens to the system and costs to customers after the 2-year term of the pilot. So I apologize. Was that Raina that, or excuse me, Zeyneb that talked about that? Yeah.
I'm happy to take that one.
Okay.
Sure. Yes. So the agreement with regulators in the approval of that pilot, it was the first gas utility demonstration of geothermal networks, set a fixed cost for the customer. It was ranging, depending on the customer class, between $6 and $25 kind of nominal contribution. It was not considered a recovery approach. And the goal of the project was to collect all of the cost data and understand how to do rate making and recovery for this technology, not to actually do it. So with that caveat, there has been a lot of learning already, not yet 1 year into operation. And the second loop has already done cost projections for a more standard gas utility style recovery. And there is an expectation that the cost per customer could remain equal to or lower than the cost of the current energy bills, with a standard cost recovery for the pipes and the thermal resources. And just in case you're asking, because there's a lot of different costs here, just in case you're asking the actual energy bills, not the fee to connect to the thermal network, all of the customers in Framingham are expecting and experiencing to date lower monthly energy bills on the electric side, including the fee for thermal per month than they had before. So I hope that's enough information, and there will be more and more information coming out as more data is collected.
Chris, do you have any follow-ups to that?
No, I'm just part of the team here in New York that's working through the proposed pilots, and cost is certainly an issue, and that's part of the utility model. I have some understandings of the Framingham pilot, but I'm not, it's all secondhand. So I just wanted to see if you had any further information.
Yeah.
My understanding is that the cost to build the system after subsidies was approximately $100,000 a customer. So it's $14 million for 140 customers, and customers vary in size, and we understand that.
Yep.
We're just trying to get our arms around the cost to build these, and how that can be spread over the rate base in an affordable manner.
Yeah. So I would caution when you do a very first project using that as a benchmark. I can tell you that the very second project has cut that cost in half per customer so far. And that there is a project also in planning that does not cover the building transition piece. And I think Jared explained a lot about that incremental every building is a unicorn piece. The interesting and instructive thing about Framingham is it took on the very hardest problem. It did not pick and choose buildings. It took on every possible permutation, including steam distribution systems and so on, in order to actually collect the data on what our old New England buildings would actually look like to transition. So, yeah, I don't want to keep going on.
Jared has his hand up, and I bet you he can add something to this. Go ahead, Jared.
My buddy.
Hey, Chris. How you doing? So you said, what's the cost of these systems? There is no like these systems.
Yeah.
It's more like, how could we strategically target, for example, a particular neighborhood that has particular characteristics in order to drive a lowest cost system, right? And that least cost item that I mentioned in my presentation, like that is so important. Least cost planning is so important in order to get these projects down. You know, and we know generally where those building typologies are that could take sort of large swaths of the territory off of gas. And I'll give you one example. Buildings that have existing hydronic distribution in them of a certain typology could transition to this in a much easier way than some of the buildings, you know, that transitioned at Framingham, for example. And those particular neighborhoods, right, might have the same exact building in them across the entire neighborhood. So think garden style cooperative in Queens, right? So you know, you could imagine 15,000 units that have this lower temperature hydronic distribution already that could come off the system in a strategic way and for very low unit cost. So I just wanted to kind of put that out there as a, you know, a framing, you know, to think about this issue.
I will add one more thing, which is the project, one of the earliest projects in the ground in Colorado, actually has all of the data showing that their costs for their system halved from the first loop to the second loop. There's a repeating pattern there, as with the Framingham second loop, and their costs were significantly lower. So there's a bunch of data out there, and I think it's very much to Jared's point that it is specific to the location and the opportunity.
So it's definitely good to hear. We know that the first run of everything and pilots are tough and more expensive, and we've gone through a lot of learnings already in New York, and we still haven't even gone through the full design process. I don't think anyone disagrees that this technology, you know, doesn't work. It's been around a long time. There's 5 different generations now. Some people argue about that. But I guess the question is, and this is what we're grappling with here in New York, is trying to create a utility scale model. And as was demonstrated through a lot of these presentations, these are already in existence. So I guess one of the things that we're trying to tackle here is, why do we need a utility involved to build these systems?
For a whole host of reasons.
Yeah.
Because utilities aren't going anywhere, right? We need that market partner who has the experience to work at scale, and also the current base of customers is all on your network. So it's all. Please, Jared, I see a hand going up. You're muted.
Finish your point.
No. I'm sure whatever I was gonna say, you can say it better. So there's a whole bunch of reasons why the utilities are really important.
Yeah, I mean, I agreed, and Zeyneb has a lot to say about this too. But you know, Ania mentioned this as well, right? There are multiple models here, right? Like we already do deploy shared infrastructure across urban environments with multiple models. Some of those look like cooperatives, some of them are municipal, some of them are like authorized authorities, for example, right? Maybe with state authority. Some of them are like enterprise funds that are created by the municipality but are technically separate. I think of New York City Economic Development Corporation as one of them. You know, and then there's the, you know, regulated investor-owned utility, which is sort of like a behemoth and probably does need to be involved, especially if we're thinking about strategically retiring particular infrastructure assets, right? So, you know, how do you do that linking? I said sector coupling earlier, but like, how do you do that appropriate linking between electric utility, gas utility, and others, et cetera, if you're not involving the regulatory process, which I think like is so necessary, right? We see this Grid of the Future proceeding happening, which is super exciting, and it's probably the first attempt to link these things. But yeah, how do we do that in an effective way if the utility's not at the table? I don't know.
I will just add that in that demonstration project in Framingham, there was a really incredibly smooth reuse of a large portion of the gas utility workforce. And I think that there is a just transition element to that workforce transition. And it wasn't just the people putting the pipes in the ground who really could do it one day to the next from gas to geo. It was also the billing, the marketing, the sales, the media, the municipal relationships, the grants of location in the street, the financing. But maybe most critical with the use of a utility is that geothermal networks and thermal energy networks all have an extraordinary systemic set of benefits and value on the life cycle. Very few cases are, a 3 to 5 year payback. They're more like a 10-year payback. And that is great for a utility financing mechanism. It is the right choice for society and has that endurance that Aaron mentioned, the continuity, reliability of service, the ability to be regulated. This is a natural monopoly. You cannot build 2 thermal networks in the same street with great effect. You will be using the same thermal sources. And so to that end, the utility model meets a kind of a wide variety, as Aaron said, a whole list of things, and I didn't even cover all of them.
There's so much nuance in that whole conversation as well, right? And Chris, like you hear these conversations that are happening in the Utenja proceeding. You've heard from some commenters about like open access common carrier models. We see in, for example, the Troy project, the Troy pilot, where there's interaction between multiple parties and the thermal energy resource is not owned by the regulated investor-owned utility. And there's this idea that, the pipes are the monopoly or the natural monopoly, but they only move heat, right? And then perhaps there's a whole private market out there that's distributing heat in.
And Jared, the thing I want to clarify is that I just gave a passioned list for a utility. The ownership of the utility is a separate thing from whether it's a utility or not. And the structure and regulation of the utility is a separate thing too. So these are very nuanced conversations, to your point, Jared. Yeah. Oh, and yes, Ann Arbor has created a local municipal utility and is moving forward with thermal energy networks or geothermal networks.
Okay, thanks. Kim, I don't see any hands up. We'll give folks. Oh, Peter, go ahead.
Thank you, Cindy. Thank you for this presentation. It was very informative. I had a question regarding Framingham. It was mentioned that there was, I guess, the first project, and then there was a second project which managed to cut the cost in half. Can you explain how they were able to do that? Was it due to the unique characteristics of the second project, or was it due to any particular lessons learned from the first project, or some combination of both? I'm sorry, I think you're muted.
Apologies. Yes, sure. We have data from Colorado Mesa University and more extensive data from Framingham. In both cases, it appears that there is a combination of what you mentioned. I'm going to very roughly, before there's any publication, say that perhaps there's about a 30% learning curve element to that first project. Every element of the workforce, every party is doing it for the first time, and there is a time cost at minimum. However, much more interesting and exciting is the reuse of some things over scale. For example, your control system. You don't build a new control system for the second loop and the third loop. You just have one from the first. So there is a set of things that are up to a certain scale, no longer an expense. And then the other part that is most fascinating is we've built a model for the technology. And when we added the second loop to the first loop, we actually needed less boreholes the minute we interconnected them, because the first loop thermally stabilized the second loop, and you did not have as much thermal resources needed distributed around the loop. And that is perhaps the most exciting element, because as you scale and you have more customers, you have more ability for load cancellation of both synchronous and asynchronous, more thermal storage in the loop itself, which flattens loads, and more ability to predict loads and really manage the thermal energy, whichever the utility is.
Aaron, you were going to say something.
Oh, go ahead. We do have one more question, but please finish if you have more to add.
Oh, no, I was just going to say exactly. So someone was able to say it better than I was. So I'm glad I handed over the mic. That's all.
Okay.
Could I just say one thing, right? So again, I was talking about that economic dispatch of thermal energy resources. That is like critically important thing to get into your head. They're not all made the same. They don't all cost the same, right? There are less expensive ones versus others. And doing a levelized cost comparison, right? And then the comparison of other benefits, I think is extremely important if you're going to prioritize which things happen first in order to reduce this peaking load, for example. I'll tell you, right, hospitals, for example, have an extreme amount of waste heat available that they currently purposefully reject. And they also have lots of that hydronic distribution pipe where they could automatically just use that pipe to redistribute the waste heat that they already have. So like that's more of like even like an operational change that they could do to significantly reduce their existing peaking gas load. So, you know, this is sort of like it's really across the board. It's like more of a broad discussion. And understanding that levelized cost across these different thermal energy resources and approaches, like that resource efficient decarbonization approach, I think is like extremely important in this conversation. You can't ignore that, and you can't jump to the highest cost sort of thermal energy resource, right? That's that catastrophic framing that I was mentioning earlier.
Thank you. We have another question from Margot. Margot asks, could you speak to the advantages of a TEN in emergency conditions like Winter Storm Elliott? So I'm not sure who's the correct person, but
can I just say that is one of the things that I had brought up, which is that this is entirely local. You're not dependent on other places or what the supply of gas is upstream. You have all control locally, and the energy is available because you're using the temperature of the earth, which is consistent, constant temperature. So you're not having to do that. And we have some examples of resiliency. I mean, obviously Superstorm Elliott is one, but across the country. And there's a great example in Texas where there was a storm, Superstorm Uri, which was more on the causing the electric side. But the point was that because everything was locally controlled, everywhere around the thermal network had a problem. And Whisper Valley, the community where there was a thermal network, had none. And then I want, Zeynep, if you wouldn't mind talking about the visit from Ukraine in terms of also sort of the resiliency of these systems and the fact that they're islandable, that would be great. But you're muted.
Okay.
I did that again. Okay. So picking up on your Superstorm Uri story in Texas, they're actually the only Oklahoma utility in Superstorm Uri that didn't have to bill its customers a special surcharge for Superstorm Uri was the one that had deployed thousands of geothermal heat pumps. So there's some really interesting cost resilience stories too. We had a visit from Ukrainian energy ministers and mayors, very interested in rebuilding some of their thermal infrastructure with thermal energy networks. It was a little bit intense to be asked a question I had never considered, which was what happens to this infrastructure when it's bombed? I said I had no data, thank God. However, it's not that different than a water system several feet down. And so perhaps they already know what the resilience of that is. And then that piece where if you do manage to get several feet down and take out a pipe, that one loop goes down, but the entire rest of the infrastructure, however large it is, does not. So that local resilience that Ania is mentioning, but also just the underground aspect and the local energy resource aspect, were the number one reason that they are now pursuing this in their hopes to rebuild in Ukraine.
Right. And I could just say that the sewers are all gravity fed. They never stop. So that energy source is also available. So if you have a thermal energy network with a combined geothermal plus wet solution, you have, even in a full grid outage, you know, I just watched 0 Day. I don't know if anybody's seen that. And I was thinking, like, if you just have a battery or a small, you know, God forbid, fossil fuel generator to keep your pumps running, you can at least move some ambient water around to keep buildings from freezing. And then you could also, you know, isolate a large community center that has the full bore of, you know, heating, cooling, hot water production, all driven by that geo plus wastewater system that's just running even when the rest of the world is going crazy. Those hydronic systems are always running.
Yeah.
And oh, I'm sorry, go ahead.
No, and Aaron, that's exactly what happened in the example Ania gave. They had some limited battery backup, and so their entire system ran on.
I was just going to say, Kim, we do have at least one more question. I know there's other stuff you want to get to, so do you want to do one more question and then get to the rest of your agenda? Or are you?
The agenda was the presentations and then an open discussion.
Oh, okay.
You know, I was hoping that the Owens team would ask some questions, but I saw Owen left, so.
Oh. Okay, well, we do have a question here from Catherine. Catherine asks, can you speak to specific hurdles or roadblocks that are impeding adoption of TEN geos and new legislation that has successfully unlocked opportunities?
So I'm going to just say that I don't think that once the legislation passes, it's been incredibly smooth. In terms of, because so many of the different stakeholders benefit from this, and because passing legislation has usually been a collaboration of all stakeholders coming together to get the legislation passed. I think the biggest challenge we have right now is that learning curve, which is everyone is doing this for the first time. So the utilities the regulators are learning about this. We're, you know, trying to find out who are the drillers that are going to be doing this. I think that, like, for example, the drilling in the Northeast, we don't currently have the capacity, but we're in the process of figuring out how to train drillers. So it's the roadblocks have been we're starting a brand new industry. So what are all the things that we need to put in place? Do we have the supply chain? So that has been happening, but since we're doing these one at a time, or in New York, 11 at a time, we'll see what what happens there. Right now, there's 24 of these proceeding at different stages, and I would say Massachusetts and New York are the most ahead. And then I think you said, what is the legislation that is successfully unlocking opportunities? Well, allowing gas and electric and water companies to be able to install, own, and operate is really opening a whole new frontier on this. There is one obstacle, which is the obligation to serve, which is if customers are saying that they only want gas, then it potentially could block a neighborhood from transitioning. For example, if you had leak-prone pipe. So that is something that is being worked on, I would say, in several states across the country, is figuring out how to do that in a way that is good for customers and would allow for this neighborhood scale decarbonization and transition. So it's both sides, it's like electrification and transitioning of the gas system.
I would also say that the Inflation Reduction Act investment tax credit has blown the doors wide open as far as large scale, project development. That I think Ania mentioned it before. It's like 30 to 50, even 60%, depending on certain conditions of a tax credit right off the top of your project. So And that can also be passed through directly to a non-for-profit. So they've removed a whole bunch of roadblocks. So if that stays in place, it's brilliant. Because again, once you have geothermal in place, I think it locks the calendar in, and correct me if I'm wrong, Jared, it's like 2035 in that range, the tax credit. And also, again, you can draw that perimeter around all of the things connected to the geothermal system, much like a wastewater energy transfer, all the heat pumps, the pipes, all the labor, all that's covered. So for me personally, for us, I've seen the Inflation Reduction Act investment tax credit be the key that unlocked the door.
That's its own webinar, Aaron.
Yeah.
Yeah, I'm sorry, we have a bunch of questions coming in now, so we got to.
And I'm just gonna
Yeah.
throw one more thing in, which
Sure.
is there's a really big connection between the barrier Ania brought up that we are hitting, which is that after you've got legislative permission, there's a real question of workforce scaling around particularly drilling in the Northeast, and that's actually driving up costs. And those costs are things we can actually drive back down again by simply having more trained and licensed drillers and more drills, which is what other countries are now doing. France just, bought a bunch of drills for the country.
Really quick too. I would say, another barrier, right? And I don't know if this is avoidable or not, but the regulatory process itself is long, and we have a very particular process to approve pilot projects and then get pilot projects built. So, we're not going to see these things operating for a couple years. And
Right.
I don't think we can wait for that.
Correct.
We need other things going on that also support this marketplace. I'd also add, right, there's a number of projects that are happening that don't have geothermal incorporated at all. So, right, think back to that whole thermal energy resource conversation. And then, additionally, we don't have the industry, okay, does not have integrators or models that can look at the neighborhood scale in the way that we need them to, okay? We have non-pipe alternatives and non-wires alternatives. They haven't been particularly effective, and we could have a whole conversation about that and why. If we could get real about focusing on specific zones to achieve specific outcomes and layer investment, right? And try to achieve as many broad goals as we can across varying organizations, right? And that might require a consortium or a coalition, right? Which we do. We do these things for other reasons. Why can't we do them for energy? If we could actually get real about doing that, we're going to see much faster adoption and a quicker uptake and understanding of what this even is.
Okay,
The
thank
average
you.
person out there doesn't know
Jared,
what we're talking
I'm
about.
sorry, but we have
Go
a
ahead,
lot
sorry.
of questions coming in. Our time is running short. So if I could ask all of you to try to keep your responses succinct so we can answer as many questions as possible. Thank you. So for Margot, she has a very on-point question that I think, I'm surprised Kim didn't write this one. How would you suggest TENs be written into National Grid's long-term plan? Which I think we would all very much like your input on.
I'm gonna go for it.
Go ahead.
And then you guys just jump in on me. Okay. So I personally would really like to see National Grid and other utilities facing the same challenges looking at the future infrastructure investment. I would like to see a multi-layered integrated planning process that identifies the electric and gas assets and capacity constraints on any given street and region, looks at the costs and savings and the energy load and demand for the region, including thermal opportunities, such as we've discussed here today, and then looks at how to optimize to get to our decarbonization goals by 2050 at the right speed, backcasting. And that's what I would call a tactical thermal transition plan. And it can be done with different values. Are we going to value upfront cost, life cycle cost? Are we going to value emissions? Are we going to value energy burden? Because when we look at the whole thing at scale, you get a very different set of outcomes than when you look kind of with blinkers on at one house or one street. So I think there's an opportunity in this conversation to look at a larger scale, and it's uncovering some things that are exciting.
TEN's integrated into IRPs, unlocking the entire value chain on the electric side, integrating electric and gas planning in a strategic way, mapping thermal energy resources, valuing them, and doing least cost planning with levelized costs of these thermal energy resources and you know, strategic deployments in order to target those specific capacity constraints, resiliency threats, or you know, peaking capacity assets like Greenpoint, for example.
Thank you. Let's go to Bess now. She's been very patient. Go ahead, Bess.
Hey, good afternoon. Can you all hear me?
Yes.
Great. Hey, Sane, I have a question for Zeyneb. And
Hi,
I probably
Bess.
should, hi. I probably should know the answer, but I just wanted to clarify. You made a comment that the customers, the participants in Framingham saw actually a decrease in their electricity or their electric bills. And I know that there was a big portion of them that were in electric resistance heat. So I guess my first question is that the main reason why they saw a decrease in their electric bills?
Oh, that's a great question, Bess.
And then also I had a follow-up question, which is knowing that, so I want to hear that answer. But if it is, you know, we're kind of missing a big piece of customers. You know, we're looking at gas customers and converting them to these, but also converting electric resistance heat customers would also free up the electric grid as well. But if you could just answer the first question and then maybe think about the second.
Absolutely. So I want to thank you for that question. So first, like I mentioned before, Framingham was designed to be learning as much as possible in one deployment. So like all different kinds of buildings and elements. So the total electric demand of the neighborhood went down. That was predominantly the driving force of that was all of that electric baseboard coming offline. So there will be projects where your total electric load for the neighborhood goes up, just not as much as if you did it with other forms of electrification. The individual customer bills is a separate thing, and the aggregated customer energy bill cost monthly was lower and projected to be lower. I mean, we haven't completed a year so far, and the projections are projected to be lower for every type of customer: oil, gas, electric, regardless. Every single customer brought onto the loop is expected to have lower, including those who are adding air conditioning for the first time. So the operational cost of geothermal, and even more so network geothermal, are simply lower. The question is, how are we paying back the upfront infrastructure? Does that fully answer your question?
It does, right. I guess I'm thinking like we're looking at NPAs and including network or TENs and NPAs, but I do feel like there's like a missed opportunity too to help with the electric grid upgrade issue if we're not just focusing only on gas customers, but we're looking at these electric to the extent that
it's got to be that neighborhood scale approach with the overlapping MTA and NWA. It has to be, right? These things have to be mapped. They need to be available between the utilities and shareable so that people can see this visually and then target specific locations. And then I think the other note, just to add to Zeynep's comment, was, you know, these systems reduce peaking cooling loads, right? So like they can reduce the summer peak. So what does that mean for electrification if we're even also reducing the summer peak?
Yeah, thank you. Okay, sorry, but we got to move on. From Scott Albertson, who is with PA Steps Consultant, can you talk about the installation process for geothermal networks, and in particular, installation challenges in an environment where significant underground infrastructure is already in place? Excellent question.
I feel like I should move this to you, Erin, and this is given out. But I'll start. So first of all, you look in downtown New York and there's nothing you can install without challenge, right? Just acknowledging that. And you know, that first Framingham project, is a less dense, easier than downtown New York project. Nevertheless, there were multiple unknown objects discovered in the process of working underground, which is what happens anywhere in New England. And any gas utility will tell you that is standard fare. The boreholes themselves are only about 6 inches wide. And so with planning and with appropriate drilling protocols, your borehole does not, it can be placed and interspersed with existing infrastructure in a wide variety of places. One of the things that Framingham demonstrated was rather than having the standard bore field that was spread out across an entire like parking lot size space, they did a directional bore field with a Schlumberger spin-off Celsius that used that oil and gas well drilling directional drill to make what looks a bit like, I don't know, an underground dandelion, boreholes sticking out in many directions from one location, which is something that gets around the challenge of a denser underground infrastructure. It wasn't necessary in Framingham, but it was a great demonstration of how we can adapt to the environment. And then I would say that there are tiny drills that can even go inside, for example, St. Patrick's Cathedral in New York, go into the basement and drill without breaking the stained glass windows. So there is the technology. The question is the appropriate use and deployment of it and appropriate costs.
Our first pitch for the Chelsea project, the U10 pilot project for Con Edison in Chelsea, was to hang the pipe under the High Line, right? And that was like the bigger vision for the full neighborhood. And the Chelsea project is a spin-off of that concept. So you don't necessarily have to go in the ground.
Okay, Scott, did you have a follow-up there or?
No, I don't. Thank you, Cindy.
Okay, let's go to John Rath. He's got his hand up. Thank you, John. Go ahead.
Thank you, Cindy. In discussions and presentations, the societal cost test, in my opinion, seems to be kind of a showstopper for innovation, and a lot of the things that I've heard the panelists say need to be taken into consideration and valued. Does the panelists have any opinions on whether that societal cost test should not be used or totally revised?
All right, no one's saying anything.
I'm not really sure how to answer that question.
Yeah.
Can you dive in with the societal cost test? I'll be honest, I just don't know what
are you speaking specifically to a New York specific societal cost test process, or generally to the concept of a cost benefit analysis in the standard way?
John, let me explain it. So the commission has a benefit cost analysis framework order that requires the use of the societal cost test when evaluating things like non-pipes alternatives compared to traditional infrastructure projects. That framework order specifies the elements that can be included as either benefits or costs. There is small amount of latitude maybe within each of those. For example, one gas utility's avoided cost of gas is going to be different probably than another, but it's fairly prescriptive. And John, I don't want to put words in your mouth, but I'm assuming that things like the fact that it does not, it has a value of the avoided cost of carbon, but not the avoided cost of methane is probably something that you think is problematic.
Cindy, this is Rick Schuler.
Yeah, go ahead, Rick.
But I thought the panelists were saying that these networks made sense just based on a regular business case. you know, without having to add in the other societal benefits.
Yeah, I think, thank you for the further explanation as we all paused. So first of all, there are absolutely cases where they do pencil out under the kind of standard operating business case that we have today within a utility payback model. And many campuses will tell you that as well. What I think is really interesting is I know here in Massachusetts, there's actually a debate going on around what goes into the BCA for such a project. And the decision for what we're going to value as a society on these cost tests absolutely does change the boundary on how many of these projects gets built. And the decision on the scale that we're going to look at for a cost test also changes the number of them that will meet it. And so I would point out that there are a lot of things that we actually care about that are real dollar values that are typically not in a cost test. For example, there is clearly a dollar value to safety. I'm sure it can be actuarially calculated what the insurance costs of a gas system are. Removing that safety hazard must have a dollar value. Yet we haven't yet, as a society, really put that into any cost test when we look at, for example, an NPA. So I think there's really a conversation to be had, even though many instances of these technologies can meet the cost tests we have today. The more we put what we actually value into these cost tests, the more we're going to get out the energy system we need.
I keep hearing a colleague of mine yelling in my ear, it's the leaky rent, you have to capture the rent. And and so there are certain organizations, right, that are better at capturing the full value stack, right, across multiple areas of benefit. I would argue a municipality is capable of doing that, as is an owner of a campus, whether that's a corporate campus or college campus. How do we unlock that full value chain across these various areas of benefit and incorporate that into this model if these investor-owned regulated utilities are going to pursue this type of an effort? I think that's a critical question.
Thank you. David has been very patient. David, please go ahead and ask your question.
Hey, okay. Yeah, hi, this is David with National Grid. I was going to ask Aaron if he had any insight into the applicability of the ITC tax credit for strictly wastewater heat recovery systems. If he had any insight into the language in the most recent guidance that adopts other underground working fluids.
So I would, as our president and CEO always likes to tell me, please consult your attorney or tax advisor. Don't take my word to the bank, but the way we've been read in, well, our technology satisfies the ITC as a standalone thermal energy storage solution because we have a wastewater holding tank that acts as a battery. The only issue with that is the calendar, I believe, on that tax credit sunsets in the end of 2025. So you got to get those shovels in the ground soon. We also qualify if you tie us again to that geothermal system. Once you have the SHARC or the Piranha as part of the geothermal system, we now qualify for the ITC. This new underground working fluids, we believe we've got an inside track, but we have not. The people who we pay to be much smarter than me have not figured out exactly all of that language yet. So we believe that it's just another avenue for us to explore. But again, this is why in addition to the business case, just from the straight economics of how geothermal and wastewater energy transfer work together from mechanical and capabilities, this ITC pairing of geo plus wet is a game changer for us. So we're always looking to pair with geo whenever possible because it's just a great system.
My read is that that's a relatively broad definition, working fluids, right? Because we see systems where even refrigerants are piped underground.
Right.
And then obviously there's hot rocks with steam, et cetera. So working fluids take a variety of forms.
Yeah.
And
it feels like they're trying to give us the latitude to make these systems work. That's our take.
Part of that other webinar that we have to do.
Okay.
Thank you.
Yeah, thank you, David. We have a question from Armand from PA. Go ahead, Armand.
Thank you, Cindy. I wanted to follow up really quickly on the BCA conversation that we just had a few minutes ago. And I would like to invite all the stakeholders to provide any data. I know these are new and there may not be a ton of data available, but any data that the stakeholders can provide on the costs and benefits of these systems, that would be extremely helpful in the BCA conversations. And the reason I bring that up is because, as you may have seen in our previous rounds of the report, we are looking very, in depth in the BCA assumptions and how the BCA studies, the benefit cost analysis are done. So I can tell off the top of my head that more than half of the total cost for any electrification scenario is coming from the upgrades that are needed to be done for the electric system. So based on this conversation that we're having, the TENs are having significant benefit to not require upgrading the T&D electric system, or even benefits for the generation side. So we would love to see if there are any data that stakeholders can provide so that we can include it in our reports on the value of the 10, so that we can have not just a qualitative discussion, but add a quantitative layer in our report.
It's a great ask, and I'll do what I can to provide data. As an OEM manufacturer, usually people take our box and then say thank you. They call us when there's a problem. We don't really get access to look under the hood to get all of the data. We do have some EPRI data coming out of a couple of projects and the Vancouver Falls Creek. So I'm happy to work with the other presenters to come up with whatever qualitative data we can provide for you. But I will admit that it's limited from my side.
There are a lot of good other organizations that are out there with resources that have attempted to quantify this, especially in the realm of thermal energy storage. And so that's certainly applicable to this conversation. But yeah, Zeyneb, you came off mute, go ahead.
And Rick Schuler has his hand up. I think Rick can probably add to this conversation. Go ahead, Rick.
I was just gonna, before I cut you off earlier, Cindy, I was gonna, I should say that, or you were gonna say that the PSC did come out with a BCA framework order in 2016 that discusses, what benefits can be included in the BCA calculation. There's only a few that the commission has monetized so far in terms of external benefits. Zeyneb brought up safety. That isn't the value of safety isn't one of those benefits that has been monetized and the monetization approved by the commission yet. It's great to discuss things qualitatively, but I guess I'm stating that attempts to actually include a monetary benefit for things that the commission hasn't approved a monetary value for might drag things down.
Yeah, I will pick that up because my inclination is to gather lots of data and then come to a conclusion after we have a lot of data, which of course doesn't go that fast. So HEET's research team has been working to quantify outcomes and benefits for as many projects as we can. We've launched a beta database for the country to use to try to build that kind of reference data. And we have a few projects where we do have numbers. I know Ania's put out a water savings summary that gives a little on that. There's the safety is unquantified anywhere. I brought it up because it's a obvious yet new item. The grid impacts, we've got a great study from and other pieces of data, including peat shaving, load factor improvements. We actually have a model for health impacts.
I was going to ask, yeah.
Carbon impacts, We don't have any numerical way to approach removal of price volatility, which is an affordability and energy burden issue. We could and don't have a resilience or energy security valuation either. So there's a lot of work to be done. That's not a great answer, sorry.
No, it is an excellent answer, actually.
The direct comparison of battery electric storage systems to thermal energy storage systems is super informative when it comes to this conversation. So I would encourage anyone to do a review of research in that space, and NREL and others have done a massive amount of work on that.
And Jared, you mentioned a study that Brattle is doing. Do you want to just say something about that?
Yeah, so appreciative of the commission and DPS staff sort of encouraging Brattle Group to do a volume 2 on their Grid of the Future study, which will include thermal energy resources and coming up with evaluation of those resources and how they could be incorporated into grid future planning. So that is really exciting. Encourage everyone to join that docket and follow that. Really cool things are going to come out of that proceeding.
Oh, I just have to throw in thermal storage because you just brought that up, Jared. We are actually trying to directly measure the thermal storage capacity to make that a monetized value as well.
Storage is everything moving forward, in my estimation. Whether you're storing it on the wastewater side, hot water, ambient water, it's going to all, or electric batteries, it's all about storage. So you can really, there's, and all the benefits of grid relief and time of day usage and all that stuff. And it unlocks the ability to do all kinds of really cool demand response opportunities as well. It's like, it's just another more financial vehicles that will help support the bottom line.
Yep.
Catherine is asking about insurance costs in regards to resilience. Catherine, can you expand on that a little bit?
Oh, just this, when we're throwing out ideas in this BCA stuff, lots of people and cities are finding that the properties are not being able to be insured because of climate risk, and so I was just thinking that is another, maybe another metric that can be measured and thrown in there, probably already being done.
Catherine, we've actually been talking to a couple of insurance companies to try to figure out if that could be an indicator for the safety and the resilience piece. But so far we haven't run into one that's actually quantified that yet.
Lenders too, right? There's a very similar conversation to be had with lenders, and we're seeing, for example, like large cooperatives in New York come up for resyndication, and they're running into trouble relating to this issue.
I just want to point out that Rick Schuler put a link in the chat for the Commission's BCA framework order. So thank you for that, Rick. Did you have anything else you wanted to add, Rick, on that?
That just has more detail on what benefits and the Commission has valued to date, and that this is the sort of controlling document on how we do our benefit cost analyses.
Okay, well, everybody, we are officially out of time, but this has been a really great discussion. Oh, and I see Jared and Zeyneb are putting other things in the chat, so thank you for that. Kim, do you have any final remarks you want to make?
Yeah, I just want to thank everybody for being here and giving this the opportunity that it deserves. I believe the 4 people that we brought to this discussion today are visionaries, and it's the kind of vision that we want to see happen in this long-term planning proceeding, because it's so crucial, and especially that we can retire the gas system. And I just really thank you all so much for allowing this to happen. I really appreciate it.
Yes, thank you.
Okay, and yeah, we look forward to further conversations. Rick, did you want to just add anything about updating the BCA?
No, we're not in the process of updating it.
Yeah.
But we sure are thinking about it more and more.
Yeah, and we have the avoided cost of gas working group as part of the gas planning proceeding. And if folks aren't familiar with that, you might want to, go to the commission's website, and I'm sure you can find information on that. But yeah, again, we're over time. Staff will be in touch about future meetings and events in this proceeding. I will just remind everybody that National Grid is scheduled to issue its final long-term plan on March 7th. And yeah, Kim, we are still working internally on the request to schedule public statement hearings. The staff on this team are not in a position to agree to that. We have to get approval for that from senior management. So we're waiting on that, and we will be in touch as soon as we know something there. Okay.
Yes, I understand. We're still going to be filing our comment, one that we we're hoping to get responses back from PA Consulting. I will say I'm a little alarmed that like the rules sort of changed in the middle of this proceeding. But I'll write you all an email, and I hope that you will also be considering our comment when we do file it, and it should be in the next couple of days.
Oh yeah, we will take comments and consider them right up until commission action on this long-term plan, which is going to be probably in the fall. So yeah, plenty of opportunity. Okay, thanks everybody. Thanks for your attention. Thanks for the contributions from the panel today. It was great, and have a great evening. Thank you.
Thank you.